appreciate the opportunity to come visit Gravitational for the first time, and also to participate in this sort of exciting and innovative approach to carrying out research programs and disseminating knowledge. So what I'm going to talk about today is some work and hopefully give you a good perspective on and give you a perspective on one part of the Stardust network, which are asteroids. And I always note that asteroids are always grouped together with the concept of orbit debris. But hopefully, as we go through the presentation, you'll see that they're actually much more than just debris. And then maybe by association, orbit debris is much more than just debris. It's maybe something interesting that tells us about our own culture, and it really is verges on anthropology in some ways. So I thought I would start off at a very simple level, and I won't spend much time here, but just to make sure we use terminology that's consistent with each other. And start off with just the idea of what are asteroids. And there are several different definitions, but the one we are using are that these are small solar system bodies that orbit the sun. And the largest one is Scheeres, almost 1,000 kilometers across, and arguably it's really a different beast than most of the asteroids that we're worried about. So it's actually large enough so it can start to pull itself into a spherical shape and the like. And a lot of the asteroids that we worry about and deal with, especially from the near-Earth asteroid population, are much, much smaller and have very different mechanics, very different shapes. And the smallest, of course, is really a grain of sand that might re-enter the Earth and you see as a meteor. They could be like small planets themselves with their own moons, with their own seasons, and their own activities, geophysical activities that change over time. Here's a nice pictorial survey of all the different, or most of the different asteroids that we visited. I'm not even showing on here Vesta, which is so much larger that it's almost not an asteroid. And in particular, I'll be talking a little bit about Itokawa, which is this little dot here, and Eros, which is a bit larger, but still nothing near as large as some of the other bodies that we've seen. And I'll be talking about a few other bodies as well. So the interesting thing about asteroids that they're not static bodies, but they actually change over time. They evolve as with the solar system as time goes on. The way they do this are through impacts with each other, and this is very important in the main belt. Once they become near-Earth asteroids, which I'll define in a second, they start to have close flybys with the planets, and they can evolve, this causes them to evolve more morphologically and also dynamically. And very interesting, it turns out that just the sunlight shining on these irregular bodies can actually form changes in their spin rates and also changes in their orbits, and actually move asteroids through the solar system through the Itokawa effect, and then through the Yorp effect. They become spun up, and they spin so fast that they can actually fly apart, form small planetary systems, and then further evolve in time. Because of these effects, what we find is that asteroids are not, in general, single bodies, and at least 15% or more of them are actually binaries or even triple or quadruple systems. And even these binaries are not static, and these are subject to creation and destruction as their lives go on. Also, in part because of this history, we believe that most asteroids are actually rubble piles and consist of the size distribution of boulders and grains from microns all the way up to decameters and larger. And if you ever talk about a single asteroid, that asteroid may actually have a very, very complex history, just like us humans, with they may be coming from different components from different families in the solar system, different protobodies, and it's all a very interesting and fascinating topic of research. So here's a snapshot from JPL of all the asteroids. We see most of them, of course, are in the main belt, but ones that we're particularly interested in, and which I believe the Stardust network is particularly interested in, are the so-called near-Earth asteroids. And we don't see quite as many of them here, in part a selection effect because they spend most of the time at aphelion. So when you take a snapshot, they don't show up as well. And so we should define what are near-Earth asteroids. And again, there are several definitions and even subclasses of these bodies, and I'm not going to get into that taxonomy. But in general, these are asteroids that have migrated from the main belt into the inner solar system. And these are, in fact, the source of meteors and meteorites that we see. Most of these are relatively small, less than a few kilometers in size. Exception would be Eros, which is probably I believe the largest, or one of the largest near-Earth asteroids. Once they actually get into the inner solar system, they don't last for very long, and because their orbits start to evolve chaotically due to the multiple planetary flybys that they're subject to. They have a relatively short half-life of about 15 million years. Some are removed by impact with the planets, and most actually impact with the sun eventually. And it's relevant to ask, how are they different from main belt asteroids? And there are some distinctions. As they come closer and closer to the sun, they're actually forced to spin more rapidly because the solar torques from radiation pressure become more and more intense. But ultimately, they're not very different from the small asteroids that exist in the main belt. In fact, the transport processes, the Yarkovsky effect, and the resonances that bring these small asteroids into the near-Earth asteroid belt actually give us a snapshot of what these small asteroids are like in the main belt, because we can't see them because they're too small for our ground-based telescopes. And significantly, these are also the most accessible bodies for exploration and also the most likely to impact. So, outside of that, why are we interested in these small bodies? And I think that there are a few fundamental reasons that motivate our research beyond just the impact hazard, although that is one of the important considerations. One reason why we're interested in is science, because when we study these small bodies, what we're really studying are the remnants of the early solar system, because these are the leftovers from the protoplanetary disk that came together and actually formed all the terrestrial and gas giant planets. So when we study them, we're actually probing the formational efficacy of the solar system. We're also interested because they've shaped life on Earth. They've delivered water and minerals to the early history of the Earth, and we believe that they cause occasional widespread extinctions from impact. That also influences life. So probably the fundamental reason at some level is why we're interested in these bodies is for science, for understanding them. Another motivation is exploration. These near-Earth asteroids are a natural destination for human exploration missions, or future human exploration missions, and the exploration of these bodies is within some of the NASA stated goals. And I believe some of the other space agencies also are contemplating continued exploration of these near-Earth asteroids. In the NASA context, they're sort of seen as a test run for a Mars mission. Even more recently, they've become of interest as a potential source of in-space resources. And there have actually been several private companies that have formed in the last several years designed for investigating technologies to exploit the resources that these small bodies present. And maybe even more famously in the last year or two, NASA's been talking about the asteroid retrieval mission, one aspect of which we actually capture an entire small asteroid, bring it back to the Earth-Moon system, or another option is we actually go to an asteroid and try to pull a boulder off the surface of it, and then bring that back to the Earth-Moon system for further study. The third reason why we're interested in these small bodies is from a societal reason. We know that small bodies continually impact the Earth. We also know that they have caused large-scale extinctions in the past. The dinosaurs especially know that. I think this is a snapshot of the Chelyabinsk, and now humanity has a better idea too that yes, these things do hit the Earth. And it's a reasonable, practical question to ask: if we detect such an asteroid on a collision course, could we stop it? What could we do? And in fact, people have been asking this question for a few decades. And there's actually a fair amount of research that's going on into various aspects of dealing with this impact hazard. Must be the president calling it. It's an asteroid in there. So it's a practical question. It's one that the dinosaurs didn't ask, right? Maybe they were just too complacent, or they were just too busy having fun. But there are a wide range of ideas and concepts that have been proposed from the scientific and engineering community for how to mitigate hazardous asteroids. And one of the more intuitively interesting ones are something like the gravity tug, and I believe we'll probably see other examples of this week. So those are the motivations for why we're interested in studying these small bodies. It's also relevant to ask, how do we explore them? And there have really been three main ways that we discover about these small bodies. First are by spacecraft flybys, and here these are all examples of images taken of asteroids during flybys. And it's a very useful way of taking a snapshot, if you will, of an asteroid. And in some cases, such as the asteroid Matilda, we can even weigh the asteroid and find out how much what its mass is. But in general, this is not a very satisfying approach to spacecraft exploration. It's as if you go to Rome and you drive by the Colosseum and you take one picture and then say, oh yeah, I was at the Colosseum. Here's the picture. Okay. You don't know much about this body that you investigate. The other way that we observe them are through spacecraft rendezvous. And this is probably the most effective way because we actually get to the asteroid, stop, and spend extended periods of time in its vicinity. And I'll have a few examples of that coming up. Another interesting way that we visit or explore these asteroids are also through ground-based observations. And later on, I'll also show you the results of some radar observations of these bodies. And while it's not the same thing as being there, it becomes very close because you have a very good picture of the entire system and models and shapes of these entire bodies. So for spacecraft rendezvous, there have been two sort of seminal missions that have framed our thinking of this. The NEAR mission to Eros and the Hayabusa mission to Itokawa. You'll notice I'm not mentioning the Dawn mission to Vesta because Vesta's, it's almost too big to be a real asteroid. It's more of a protoplanet, right, or a dwarf planet. The Near-Earth Asteroid Rendezvous was a NASA space science mission, visited Eros, launched in '96, arrived in 2001, and actually landed on the asteroid in 2002. Very simple spacecraft, very effective at what it was doing, and it captured some really amazing imagery of this asteroid. It starts to give you some idea about how non-intuitive their shapes can actually be. And this is very interesting. So it's about the size of Manhattan. And in fact, this is, for scale, the Empire State Building compared to the surface of Eros. And it's interesting, you actually see that there are actually boulders on the surface resting that are not as big as the Empire State Building, that are reasonable, fractions, a couple, maybe 10 stories of the Empire State Building. Another interesting mission is the Hayabusa mission. This is the Japanese sample return mission to the asteroid Itokawa. Launched in '03, arrived in '05, and returned to Earth in '10 after a very long, interesting journey. This is an image of it re-entering, bringing its sample back to the Earth. This is an artist's depiction of the sampling events on the surface of that body. And this is an actual snapshot sort of a self-portrait of the asteroid or of the spacecraft at the asteroid, where you actually see the shadow that the spacecraft casts on the surface of the body. So here is the body that Hayabusa visited, the asteroid Itokawa, and for comparison, here's a picture of the space station. If you remember the previous picture of the asteroid Eros and the Empire State Building, this puts it into context. The Empire State Building could effectively fit inside of the asteroid Eros. So if you bring this small asteroid to Eros, or the Empire State Building could fit inside of Itokawa. But if you bring Itokawa to Eros, you realize it's just a small clump of rocks that you wouldn't even notice on the surface of this larger asteroid. And this is actually a property that asteroids have. They're at some level self-similar collections of debris and boulders and gravels that span the size from tens of meters up to hundreds and hundreds of meters, if not kilometers. So here's some more snapshots of Itokawa. This is one of the samples that were brought home. This one is about, I think, 50 microns in length. And we believe this body consists of collections of a size distribution of particles as small and smaller than this, all the way up to the larger boulders that we see strewn across its surface. And actually, this morphology has a lot of implications for the strength and evolution of these small asteroids. Now, our exploration activities to asteroids are continuing in the future. There are actually a few missions that are set to be launched in the next several years. Hayabusa 2 mission from Japan will actually be launched at the end of this year if everything keeps on track. Another mission that I'm involved with is the Osiris-Rex mission, the asteroid sample return mission, which will go to a primitive asteroid, take a sample and bring it back to Earth. It's led by Dante Loretta, the principal investigator at University of Arizona. And Osiris-Rex is a sample return mission that brings back some samples of pristine carbonaceous regolith from the asteroid Bennu. And it's currently in phase CD, which means that they're actually building the spacecraft and constructing it. We launch in 2016. We get to RP36 in 2019 and return back to Earth in 2023. And of course, like all NASA projects, Osiris-Rex is an acronym. It stands for Origins, Spectral Interpretations, Resource Identification, Security, and Regolith Exploration. So all of these concepts are built into the science goals of this particular mission. So seeing a snapshot of what some of the different exploration missions that we've had are, it's relevant to ask what are the challenges that we face when we go to these small asteroids and in order to explore them. And I'm not going to talk much about this, but I just want to emphasize this aspect of the problem because the small body dynamical environment, I think you can strictly qualify it as one of the most strongly perturbed environments that we can find in the solar system in terms of a place where we can bring a spacecraft and have it interact and actually have it carry out useful exploration functions. And hopefully as I present some of these examples, you'll get a feeling for this. But asteroids really present extreme exploration environments. We have gravity and rotational effects that can destabilize orbits in very short timescales. Something as small as solar radiation pressure perturbations can actually strip a spacecraft out of orbit or fundamentally destabilize its motion. And when we start to couple these perturbations to each other, we have strongly chaotic orbital dynamics that we can experience. It also turns out that the unique formation and evolution histories of asteroids create extremely non-intuitive systems that sort of challenge the way you think about exploration and think about different environments that we can experience in the solar system. And what I like to use as a case in point is what turns out to be a very typical binary asteroid system. is 1999 KW4. And this is an example of what a radar observation can provide in terms of understanding asteroid environment. So we've never visited this asteroid. In fact, this asteroid is probably one of the most expensive NEAs that we could ever hope to visit, because its perihelion is down around Mercury, and its aphelion is up around Earth. So it takes tons of fuel to visit this guy. But through radar observations, we can actually construct this very detailed and very informative model of the system. And when you look at this system, you realize it's a binary asteroid, and you also realize it's just like the Earth-Moon system, right? Because the larger body is slightly oblate. It's got a little bit of a tilt to its rotation pole, and it spins much faster than the orbit of the secondary. And the secondary actually librates a little bit relative to its otherwise synchronous one-to-one orbit, and always shows the same face towards the primary body. Of course, there the analogies fall apart, and even though it's like the Earth-Moon system, it's very much not like the Earth-Moon system as well. And in fact, if we start looking a bit closer, especially just at the primary body, we can really realize how non-intuitive this particular body is. So here we have pictures of the primary, and this shows the slopes across the surface of this body. And here the gravitational slopes go from near zero all the way up to 75 degrees, where you see these little red points here. What we see is most of the asteroid is actually steeply sloped at an angle, of around 30, 40 degrees. So you have to be a little careful when you walk across the surface of this particular body. If you slip, you might fall. And even more interesting, if you actually look at the local gravity across the surface, and here this is really has to be the addition of the gravitational attraction plus the rotational or centripetal acceleration across this body. You find that it's even a little bit more odd, because as you move across the surface, you actually go from essentially a weightless environment at the equator of this body up to its maximum gravitational attraction at the poles, which again is only 0.3, 0.4 millimeters per second squared. So down at the micro or less than milli-G level. So this tells us that this particular body is actually spinning so fast that at the equator you're almost weightless. Another aspect of the body, which is due somewhat to its shape, but more just from the geophysics of motion on small, rapidly spinning bodies, is that the lowest point on the body is also turns out to be the furthest point from its center, which is very non-intuitive in terms of geophysics. And in fact, the lowest point on the body is the equatorial region. And here we have the surface slopes mapped across the surface of the body again. And these little arrows point in the direction that a marble would roll if you let it drop onto the surface. And you see in the northern hemisphere, all marbles roll towards the equator. And in fact, in the southern hemisphere, all marbles roll north towards the equator as well. So at this point where we have near 0 G is also the point where all the loose material wants to migrate on this particular body. So if you are an astronaut and you step on this body and you slip and fall, it's a very steep slope, and by the time you roll downhill toward the equator, you're probably going to be in orbit flying around this particular body, because the gravitational attraction is near zero down. And in fact, we can quantify this very explicitly, and we'll show you that the particles on the surface of this body can be meters or even less from being in orbit. So here, this is a plot for the primary body of the sort of the geosynchronous orbits around this particular body. These are orbits that have orbit period equal to the rotation period of the primary. And we see because of the equatorial region is a bit misshapen that these don't line up nicely along the principal axes of inertia, but they're actually shifted off a little bit. But we still have the usual structure of two saddles and two centers. All of these orbits, in this case, are unstable. But if we superimpose the radius of the body on top of here, we see, in fact, that these equilibrium points, in fact, limit the size of this particular body. And if you were on the surface of it and wanted to launch something into geosynchronous orbit, you could literally just reach up, let go, and it would be in geosynchronous orbit. So we see that we do have material that can be presumably spun off the primary, but what we also find, and we have to remember this is a binary system. If we go back to the three-body problem and actually plot the energetics of material coming off of the surface, and we can come up with an analogous zero velocity curves here. They're approximate, but the concept still holds. If you actually spun material off the surface, it's actually trapped by the zero velocity surface, and in fact will return back to that surface again. So it's a very, if you just think through the dynamical implications of this environment, you realize it's a very complex place. And you have strong mixing between non-intuitive geophysics, restricted three-body problem in this case, and you have to start asking questions about mechanical and material properties of level pile asteroids in this extreme environment. So there are other challenges as well, I mentioned, such as gravitational effects. Here I'm just showing, these are some simulations of orbital motion around the asteroid Eros, just to show you how very relatively small changes in initial condition can give you huge changes in outcome. In particular, here we have, these are inertial plots, although I'm just showing Eros at the initial condition. Sorry, at the final condition for this run. But here's a very nice stable orbit, this red one. And actually all we did is we started this guy in a local circular orbit and let it evolve, and it would stay in this orbit for very, very long periods of time. Then we start playing around with the initial condition. If you just move in a few kilometers and start it in a circular orbit there, you get this green trajectory. Sorry, we get this blue trajectory. So this is starting at a circular orbit about 5 kilometers closer in. And we see it goes around once, gets pumped up in energy, and comes back and impacts pretty much within 1.5 orbit periods. So that's probably not what we would like to see. And if we also just rephase the initial condition, so we start on the local circular velocity, but we just rephase it by 45 degrees and start in this condition relative to the initial orientation of Eros. And in this case, we see we go around once, twice, and then actually get ejected in a hyperbolic orbit. So this is just from the effect of the non-spherical gravity field of this particular body. So sort of moving from the surface, which the binary asteroid example was looking at, this is moving further off into orbital space. We find very, very sensitive dependencies on initial conditions, a very chaotic system. And if we actually make our asteroid smaller or go to an even larger orbit, we start to find the strong effects of solar radiation pressure on orbital dynamics as well. And here's a couple examples of an orbit around a small point mass. And here we just have, we're starting off our orbit in a local circular orbit again. It's a rotating frame with the sun is off on the left-hand side. And we have two trajectories with only a 100-meter difference in initial conditions. And you see that for the inner one, the orbit is strongly non-Keplerian. It actually swings back and forth in a very systematic way and eventually impacts on the surface. You just move 100 meters further out and start that orbit, it actually immediately escapes from the system. So again, another example of how the initial condition space for orbital dynamics around these bodies is extremely sensitive. One more effect. Here we have an orbit that we've launched around this small asteroid that seems to be quite stable. It's a circular orbit. It stays roughly fixed, although you can certainly see that it's pushed back from the orbit plane. This is from the solar radiation vessel. This is the view from the sun. This is the view in the terminator plane off to the side of the system. And what we find here is that this asteroid itself is on an elliptic orbit around the sun. And in fact, as the distance between the asteroid and the sun varies, the escape radius of an orbit around this body actually varies as well. In this particular case, we're on an elliptic orbit, but then as the asteroid comes into perihelion, it gets too close, if you will, and the spacecraft gets stripped out of orbit just from the solar radiation pressure effect. So from this example, you can say, just because you're in an orbit that seems to be nice, safe, and stable now, you can't make strong predictions always about the future of that orbit and how stable that's going forward in particular. So it's a rational question to ask, how can we deal with these exploration challenges related to the close proximity dynamics of spacecraft and exploration vehicles around these small bodies? You can go into more detail on this, and I've given other talks and written many papers about this, that really as a function of size, shape, and spin state of the asteroid, you find very different behaviors of a spacecraft in that environment, and it really led to very different sorts of approaches to exploration and to your close proximity mechanics and dynamics around that body. And there are several ways to sort of cut up the system in order to dissect it and understand what different approaches need to be taken. Here are a couple of significant regimes of motion, if you will, that we have to handle either separately or in combination. We call it the gravity regime, and here the orbit mechanics are really controlled by the mass distribution and rotational dynamics of that central body. Solar radiation pressure regime, where the orbit mechanics are controlled by radiation pressure and the gravitational tidal perturbations from the sun. If we get into multiple orbit systems, we have to deal with simultaneous perturbations from multiple gravitating bodies. If we go visit a comet, such as the Rosetta mission is doing now, or preparing for, we have to start dealing with additional non-gravitational effects just from the comet outgassing, acting and impinging on the body. And in some cases, such as the Japanese Hayabusa mission series, they actually have made an engineering decision to not try to carry out orbital mechanics at these bodies, and you can go entirely to a controlled and hovering motion approach where you essentially try to kill all the attractive forces and all that arise from that asteroid and try to directly control the spacecraft in that environment. And in some instances, that's a very attractive way of going, although from a scientific perspective, in terms of measuring the mass properties of that central body, there are some real drawbacks from this sort of approach. So the one mission that I'm involved with, the OSIRIS-REx mission, we're going to an asteroid called Bennu, which is shown here in this movie. And in fact, for this particular mission, we're taking an orbital approach toward our exploration activities. And one of the mainstays of that are these so-called terminator orbits that I showed some examples of previously, where we actually place the spacecraft into orbit plane that's in the terminator plane. So this is the view from the sun towards the spacecraft. And this is a view looking at the side. The sun is off towards the right in this case. And you can see the natural dynamics of these orbits are in fact to follow the sun. And they're experiencing orbital torques on the orbital plane that actually cause this orbit to precess and to keep synchronized with the sun. Even if this asteroid were on a highly elliptic orbit, the mechanics turn out in such a way so that this guy will always be very close to the terminator plane of that body. So as Max mentioned, we've studied not all aspects, but many aspects of this close proximity motion around bodies, and have a book that's been out a couple of years that explores some aspects of this. And if you're interested, you could go there to see some of the work that we've done. Although there still is a lot of research being done, I think there's still many open questions about particular systems, how you can best explore and carry out close proximity operations at these bodies. Now, so that's sort of an overview of an exploration side. But the exciting thing about the study of these small bodies is that they really push you to go further. And if you really want to understand what it takes to explore the small body environment, you have to, in fact, expand your own toolkit and start asking fundamental questions that remain unresolved, and essentially pursue scientifically additional areas of research in order to fully understand what it takes to operate at these small bodies and what their fundamental properties are, what things you should be worrying about when you go to directly interact with them. So in my own career, this has been a great opportunity to really push myself into different areas of science and investigation in order to pursue some of these fundamental exploration issues. But what does it really take to explore, to operate, and to interact with a small body system? So in this slide, I'm sort of raising some of these questions that if you really want to understand how to explore small bodies, you have to answer fundamental questions across really a range of fields, from astrophysics and astronomy and celestial mechanics, which are pretty obvious, but even into things such as granular mechanics in space environments and microgravity environments. And of course, you need to understand the mathematics, which are peculiar to these sorts of systems. Further, I believe the properly developed techniques for exploration and utilization really requires us to understand how they've changed in time, because that tells us what state they may be in now or what state they could be in the future. You need to understand their geophysical properties, their formation circumstances, since we believe that some of these asteroid systems are reformed many times over their lifetime. We can't assume that everything we see is primordial. It might actually be very recent. And fundamentally, these things inform how these bodies will respond to external stimuli, or when we go to interact with them. How are these bodies, in fact, going to react? So here's a simple example sort of showing one of the processes that we believe is at work for evolving asteroids. And here we have essentially a rubble pile of bodies, a bunch of grains that we piled up onto each other. As I said, the York effect actually causes asteroids to spin at faster and faster or slower and slower rates as time goes on. And here we're really doing an experiment where we increase the spin rate of this asteroid in a systematic way, and depending on certain parameters of the system, we find out where does the body start to fail and come apart. Here we're tracking the interior pressures of this body, and here's like a Drucker-Prager failure envelope, and we're trying to determine exactly at what point does this collection of bodies actually fail and come apart and maybe form a binary system. So here in this experiment, we keep on spinning it up, and eventually, as a function of its material properties, it can actually split into several pieces and continue its evolution. And there's actually a lot of scientific and astronomical evidence that this is a process that seems to happen fairly commonly in the solar system. So in order to understand how they respond, and this is an important point because the current plans for exploration and mitigation really go beyond what we've done before with these bodies, which is to rendezvous with them, maybe touch their surface, and have some extended period of close proximity operations. What we really need to do in the future, and what our plans are to do in the future, are actually to deliver and operate pods and rovers to the surfaces of these bodies, to capture entire asteroids, if you will, or even come down and pull larger boulders off of their surface. And it's fundamental to understand how these asteroids will respond to these interactions. And what that really fundamentally depends on is what are their mechanical properties and what are the mass morphology of these asteroids. And we can raise some very fundamental and important questions such as our small asteroids monoliths. I think when I first started working in this field, I thought, well, if the asteroid gets small enough, it's just a big boulder, like you might see in the mountains. Okay. But can they actually still be rubble piles, even if they're a few meters across? And actually, there's very strong evidence now that some of the smaller asteroids that we see are in fact still rubble piles, even if they're spinning fast. And that seems counterintuitive, but we'll talk a little bit about that. If we have a very small asteroid, does it still have regolith? Does it still have a surface covering, or is it just a bare rock? And how much surface covering could it actually have? These become very important considerations from an engineering perspective if you start talking about going and interacting with these bodies. Do you need to worry about dust, or do you not need to worry about dust? And even more fundamental, how strong is an asteroid? Okay, how much pressure can you place on it before it may actually break? So the work that we've been doing most recently is really trying to address these fundamental geophysical questions, really, based on the best available data that we have in scientific theory. So one of the questions at the heart of this is are asteroids rubble piles, and to what extent are they rubble piles? And even a decade ago or so, everything seemed to come into focus on this based on a series of plots that Peter Pravik and Al Harris came up with in the early 2000s. And I'll just go here. And this is a very famous plot that you've probably seen. This is rotation period of asteroids versus their diameter. So here we have the diameter of asteroids. Here we have the rotation periods. And there's two things that jump out at us. That there's a spin limit on larger bodies, a little bit larger than a few hundred meters. And once we get below that size, there seems to be no spin limit at all. And all these bodies seem to be spinning very, very fast. So you can have the super fast rotators that are small and spinning with periods less than an hour, less than a tenth of an hour, just a few minutes spin period. And these larger ones with this other deformation rate. And the interpretation that most people had, myself included, when we look at this, is that okay, maybe all these guys here are rubble piles, and when we spin them up to a certain rate, they just fall apart, and then all the rocks that they were consisting of are all these small guys that seem to be spinning really fast. But as time has gone on, and as we've probed the mechanics, the dynamics, and the geophysics of how a rubble pile responds when it gets spun up, we've actually changed, at least I have, and given my research group, changed their perspective on this. And we're actually thinking now that while this is, if you will, a spin limit for the large bodies, these smaller guys could still be rubble piles. And we can't just rule it out. So just because you want to go visit a small 10-meter asteroid really doesn't mean that it's a rubble pile. And it's just going to be one big, doesn't mean that it might just not be one big boulder, but it could still be a collection of smaller rocks. So this sort of motivates the question of what is a rubble pile? And technically, it's a size distribution of boulders and grains. And it extends from microns, like here, the Itokawa sample, all the way up to boulders that could be a couple hundred meters across. There are some larger boulders, narrows that would sort of qualify in terms of that size. Measurements of Itokawa indicate it's roughly a 1 over d cubed size distribution from millimeters to decameters. And from analysis of the sample, it's also 1 over d cubed from microns to millimeters. Whether these two size distributions are connected or not is an open question. So what that means is for every meter-sized body, there are 1,000 decimeter-sized bodies. For every decimeter-sized boulder, there are 1,000 centimeter-sized boulders. And so you get very, very steep size distributions. The smaller you get, the more bodies, the more gravels you actually have. What this implies is that fines, or the small particles, in some sense dominate in number and at least in surface area over larger grains. And it really implies that larger boulders are placed or covered or connected to each other in a matrix of these finer grains. There's actually some interesting consequences of these boulders being imbued in this matrix. In fact, this matrix can serve as a very weak cement that can hold larger blocks in place. And if we just apply basic properties of cohesive grains measured on Earth and the Moon, it actually provides some specific predictions for the cohesive strength of a rubble pile body. So here are some experiments that we carried out, numerical experiments, where we actually place a bunch of regolith between 2 meter-sized boulders. And one of them is a cohesionless regolith. The other one, we just give it a cohesive van der Waals forces that exist ubiquitously on Earth between smaller grains. If you ever worked with flour, if you like to bake bread, you know that flour has very distinctive mechanical properties. That's because it's a cohesive powder. Okay, you can stick your whole finger in there and it retains the whole. Very different than sand. The sand is a little bit larger, and the weight of the sand grains is large enough to break those cohesive bonds. Now, in a microgravity environment, however, those ubiquitous cohesive bonds can become extremely important and start dominating over the weight of the boulders and the other materials that are held in place. So in this particular example, we have these two cohesionless, cohesive regoliths, and if you just pull on them, do a little stress test, the cohesionless case separates right away as soon as you get larger than gravity. The cohesive case, it actually makes it a bit stronger, and you have to pull a little bit harder in order to bring these boulders across, bring them apart. So we can actually develop a theory for how this process works. And it comes down to a number of fundamental parameters. Maybe the most important one is the mean particle radius, or the dominant size of grains in the regolith, which tends to be, we believe, at least less than 100 microns, maybe as small as 10 microns. And you actually get a yield strength for how strongly boulders are tied together. If you go through the numbers, you come up with a ludicrously small number, about 25 to 150 pascals. And that's nothing. I mean, we can't generate that weak of a bond on Earth practically, just because the weight of materials tend to overwhelm this very weak effect. However, if we bring that weak effect into the asteroid belt and start to understand at what point asteroids would start to fail or start to pull themselves apart as a function of their size, we actually see that this very, very weak strength can actually have a big consequence in the asteroid belt. So here we have this figure again of asteroid diameter versus rotation period, and I've overlain on it a couple of different sizes or strength limits that are derived from a simplified analytic theory, where we can sort of specify the strength of this cement that we believe holds these boulders together. And if we tie this to properties of lunar materials, if we have strong lunar cohesion, that's about 3 kilopascals. And if rubble piles had this level of strength, we would actually expect to see a lot of rubble piles in this region here, where we don't see any. If we have weak lunar cohesion, which is at 100 pascals, even here we would still see probably more rubble piles in this region here. But if we go all the way down to a very weak cohesion of just 25 pascals, we still see that this is more than enough to strengthen a rubble pile when it gets smaller than 10 meters to extremely rapid spin periods in the order of minutes. So this is just a theoretical calculation, but we can actually go, and it suggests that maybe the monoliths are the guys that are truly really fast spinning. But even here, they don't need much strength to stick together. And all of these guys could actually still be rubble piles. And that has a lot of implications if we want to go out and explore and mitigate these bodies. There's actually a couple of other lines of evidence that suggests that such a weak cohesive matrix may exist at these bodies. One is if we look at the binary population, what we find is that there's actually a statistically significant cutoff at the lower size of asteroids. We don't find binary asteroids less than a couple hundred meters across. And the radar observations should have detected these. We can actually tie this to a level of cohesive strength in these rubble pile bodies. As we have a strong cohesive strength, we have to spin them up so fast before they fail that they would actually be at escape speeds when they fail. So that once they break apart, they would actually immediately escape from each other. And if the strength were at 3 kilopascals, we would expect to find no binary bodies less than this size because they'd have to spin up even faster and faster before they escape. So here, this line is the escape spin limit. Even at 100 pascals, it doesn't seem to be strong enough, but something at the order of 25 pascals, what we find is below this limit, we have a dearth of binary bodies. So the weak cohesion is consistent with the small binary cutoff. And there's another implication as well. Fission should lead to fast rotating tumblers. We have a uniformly rotating rubble pile, and if it does break and it's spinning fast, what happens is that it immediately starts to, it produces two bodies that are in complex rotation. Because the spin period in general is preserved across this splitting, but the mass properties are not. So even though the spin vector is in the same direction, the moments of inertia after it breaks apart are actually in some random direction, so these guys immediately start to tumble. And even though it's a very hard measurement to make, there are some of these small asteroids that have been detected to be tumbling. And if we line these up against these strength limits, again we find that it's consistent that these small, rapid tumbling bodies could have been formed from a cohesive body that was spun so fast that it failed. And one very significant example is the 2008 TC3, also known as the Alma-Hattusila meteorite, which was observed before it re-entered the Earth, and it was seen to be only about 10 meters large, but it was tumbling. They know from its meteorite fall that it was definitely a rubble pile because it was comprised of many, many different types of meteorites that shouldn't exist in one competent body. And there's other evidence as well, but it's also right up against this spin limit. So it's really at the limit of how fast it can spin. Finally, how much more time do I have? 7? Finally, we can ask, do these cohesive forces have an implication for the surfaces, even if we do have, and some of these bodies will of course be boulders, do these cohesive forces still play a role for finer grains on the surfaces of boulders? And here we can carry out a simple analysis where we keep the cohesive force that we're talking about, gravitational, and then the inertial forces, and come up with limits for how fast you must spin a body to shed materials of a certain radius off of the body. And what we find, here again we have all of these asteroid diameters, rotation period, and now I've plotted on here how fast you need to spin a body in order to shed grains of different sizes from the surface of a boulder, if you will. And what we find for all the documented asteroids, seemingly you could still have millimeter-sized grains strewn over the surface, and the cohesive forces, and this is cohesive forces based on lunar regolith, measured lunar regolith properties, should in fact be strong enough to bind those guys on there. They might be very tenuously held. If you went there and if you wiped it, or smacked it, they may come off. But when you get down to smaller size grains, 10 micron size grains, you have to spin these bodies extremely fast to just drive off this very fine material. And we're all familiar with this. If you have a dusty windshield, you know it doesn't matter how fast you drive, you can't get the dust off the windshield. You've got to go and mechanically remove it. Slightly different process, but it's a sort of a similar effect. So the prediction is actually, even for monolithic boulders that we may visit, they may still have a very dusty environment on their surface. This has a lot of engineering implications because this dust is pretty nasty stuff. So a couple more slides. So those last few slides sort of trace some of the really the geophysics sorts of investigations that trying to understand better how these asteroids respond have motivated. It's also interesting to realize that there are many other avenues of exploration that come out when you start asking these fundamental questions for these interesting small bodies. And another slightly different one that we've been looking at lately is actually much more mathematical and really falls more into the realm of celestial mechanics and granular mechanics, and where those two fields of study combine. And that is, what is the stable configurations for a collection of self-gravitating grains? So it's a very simple question to ask, actually a very simple question to start to analyze, although it turned out to be very rich. And this is fundamentally motivated by observations. So here again we have Itokawa, and these are some images of this smooth gravity part of the body. But if you look at images from other parts of the body, and these are images from this region here, you really see that this guy looks like a bunch of rocks resting on each other. It's a pile of rocks, self-gravitating. Okay. And so you can start asking questions, well, what's the stability of a self-gravitating pile of rocks like this? And to do it mathematically, you have to make it really simple. But even turns out these simple things have sort of non-intuitive results and starts to lead you thinking about problems in slightly different ways. For me, it's really changed the way I think about celestial mechanics, and it's actually given me some additional tools to analyze celestial mechanics systems. So if we take that question, what's the stability of a collection of self-gravitating grains, and we just bring it to the three-body problem with equal size distributions, what we find is that we actually have this whole much larger set of equilibrium configurations that actually exist. From the three-body problems, we know, the only equilibrium solutions that exist are the Lagrange and the Euler solutions. Okay, as soon as we allow these guys to be finite density bodies that can rest on each other, you actually expand the whole realm of possible configurations to include ones where they're in contact. Here, for the three-body problem, we pick up 5 additional relative equilibrium configurations, only 3 of which can ever be stable. And in fact, the stability of these guys actually changes as you change the spin period or the spin rate of this collection. You can actually bring this up to the 4-body problem, and it starts to explode, and you get much more complex systems. Here again, the ones in the boxes are the only ones that can actually be stable as you start to spin them up faster and faster. And ultimately, we'd like to explain something like this, where we have this collection of grains that we spin up, and we'd like to understand what causes the transitions in stability as we increase the spin rate, and what causes the points of weakness, and why does it settle into these particular configurations at particular levels of angular momentum. And even for the 2-body problem, if we go away from having spheres, as I had in the previous case, and just model these guys as ellipsoids, and start asking what happens when we spin something as simple as this to a what we call the disruption rate, where the 2 bodies go into orbit around each other, we find extremely exciting and complex dynamics that really cry out to be analyzed in a very rigorous way using rigorous tools of inquiry. sides. This is just a really movie. Here, this is a rotating frame where these two bodies are always connected on the center of mass. And what you see is a relative rotation of these two guys. So just a final slide with some summary and conclusions. First of all, and I hope the examples I've shown have motivated this, asteroids are diverse worlds and they merit our attention. They also present severe and extreme environments that challenge our notions of dynamics and mechanics, but can definitely be understood and explored. And in fact, there are many different ways that we can carry out close proximity operations about these bodies in order to further explore and utilize and mitigate these bodies. Also, it's interesting to note that the very non-intuitive properties and behaviors that we see for these bodies can actually be explained and analyzed in terms of very simple material properties such as cohesion, gravity, and other forms of mechanical effects. Also, when we apply these properties, we find significant challenges for future exploration, exploitation, and mitigation missions to these bodies. I haven't really touched on this, but some of the current research we're doing is actually exploring how unstable the surfaces of these bodies could be. So that is there a way that you can tell for a particular asteroid, if you come down and touch the surface, might you cause a landslide in this microgravity environment and actually fill space around the asteroid with debris over some period of time, trying to better understand how we could tell whether or not surfaces are covered with adhering dust, and further increase our toolbox, if you will, to other exploration approaches and techniques for some of these very extreme bodies that we wish to visit in the future. Okay, so with that, I'll be happy to answer the questions if any of you have.